Now in the earlier lecture, we already learned about all the different parameters and all the different, we can say, multipliers and factors that needs to be calculated when we want to calculate the wind loading on a particular structure as per AS1170. Now in this lecture, we shall try to solve a practical example. And in this, we shall solve, we shall go through all the steps and we shall go through all the factors that we have calculated. And according to that, we can simply, find out how we can calculate the wind pressure. First of all, when we're talking about the AS1170, first of all, we want to calculate the, or we can say the first parameter that needs to be calculated is the regional wind speed. So, as we know that regional wind speed is basically based on the peak gust wind data of 3-second interval. And the second step, that needs to be referred is that we do need to find out the return period. So, return period, the one that we have considered here for service life, that is basically 25 years, and for ultimate we have considered 1000 years. So that is the first assumption that has been made, that we are right now talking about the 1000 years returns period, or we can say 1 upon 1000 as the annual probability of exceedance of a particular incident. Now when we are talking about the wind region, let us say the region is basically wind region C. So regional wind speed, that shall be basically different. So for serviceability it shall be different, and for ultimate it shall be different. So if we refer to the table of the VR that is given in the AS1170, basically both the things are given. Either, we can simply find out these values from the table itself, or we can calculate that with the help of this particular formula. That is 122 meter per second minus 104, that is the fixed number, into R service of minus 0.1. So that simply, gives us the value 47 meter per second. And if we're talking about the ultimate time interval, so what we shall do is that 122 minus 104 into 1000 times minus 0.1. So whatever is the value, this value is that shall be basically 70 meter per second. So that is how we can find out the regional wind speed at serviceability limit state and at the ultimate limit state. Now, first of all, if we're talking about the wind direction multiplier, so it has been assumed that we're talking about the, the most conservative case. So MD value has been taken as 1. Climate change multiplier, that has been assumed as 1.05, as we are right now talking about the wind region C. So after that, when we are talking about the terrain height multiplier, so terrain height multiplier, when we're talking about the terrain category, so terrain category we can assume it as 2, and height we can consider as 15 meter. So for terrain category 2 and height z equal to 15 meter, that's terrain height multiplier as per the table that you can refer to the AS1170, that value shall be 1.05. After that, when we're talking about the shielding multiplier, so let me just revise the points here, because we are having all these values here. So first of all, we find out the value of the return period as per the National Construction Code of Australia. After that, as per the input or as per the city known, we have simply find out what exactly is the wind region. And on the basis of the return period, we can simply find out the regional wind speed at serviceability limit state and at the ultimate limit state. After that, wind direction multiplier, that has been assumed as maximum as 1. Climate change multiplier as per the wind agency has been considered as 1.05. Now we are talking about a terrain height multiplier. So terrain height multiplier, assuming that terrain category is 2, the height is 15 meters. So as per that, basically specify terrain height multiplier value shall be 1.05. So the next point here. So the next point here is basically the shielding multiplier. So shielding multiplier in this case, basically when we're talking about the average roof height of the structure being shielded. So we know that the height of the structure is 15 meters. Number of upwind shielding building, let us assume that NS is equal to 3. So average spacing of the shielding building, we know the formula, that is LS is equal to H multiplied with 10 upon NS plus 5. So that gives us the value of 125 meter. Average roof height of the shielding building, HS, we can consider it as 10 meter. Average breadth of the shielding building, that also we can assume it as 5 meter. So shielding parameter S is equal to LS divided by square root of HS into BS. So LS we have calculated with the help of this particular formula, where we have entered the HS 15 meter, 10 upon number of shielding building as 3 plus 5. So that gives us value of 125. So that LS is entered here, that is 125 divided by square root of HS. So HS we know the value as 10, and BS also we know the value as 5. So simply, we can find out the value of the shielding parameter S here as 17.7. So as per the 17.7, we can refer to table 4.3 to find out that MS value is 1. So this is clear to us. After that, the main, calculation that we have studied in the earlier lecture, that is a topographic multiplier. Now, topographic multiplier, needs to be understood, and it shall be better if you can open the code also in front of you. So for the first parameter, the first input that we have assumed is that the height of the hill, the one that we were considering, this height, this has been assumed as 60 meters. After that, horizontal distance upwind from the crust, that is this particular distance, LU, that has been assumed as 36 meter. So in reality, you shall be having the data, but we are reading the theoretical examples. We have to assume all these data. So length scale L1. So L1 is basically given in the code as 0.36 LU. That is a maximum of 0.36 LU and maximum or 0.4 H. So this value comes out to be 24 meter. After the second value, that is L2. Now L2 here, if we are referring to, L2 is basically 4 times L1. So whatever is the value of the L1, length scale L2 is 4 times L1. So 4 into 24 gives us the value of 96 meters. Now you need to understand that when we are saying that L2, that is length scale L2 is equal to 4 times L1, that is valid for upwind for all types. And for if you're talking about the like for hills and ridges and escapements, upwind also and downwind also, the L2 value is equal to 4 times L1. But when we're talking about the escapement, so for escapement, the L2 is basically 10 times L1 only for the downwind, not for the upwind. For upwind, it is again 4 times L1. So in this case, as we are assuming the hill case, so L2 value is we have considered as 4 times L1. So L2 is taken as 4 times L1 for upwind for all types and downward for hills and ridges, or 10 times L1 downward for escapement. So that was the concept that I should try to explain to you here. Now, if you're talking about the reference height above local ground level, that is the height of the building above this particular level. So this we have assumed as 15 meters. Because if this height is 10 meter, then by default, the value of this particular, topographic multiplier MT shall be taken as 1. Now slope h upon 2 LU, this value comes out to be 0.83. If you remember, if this value is less than 0.45, then again, the ground is practically flat. So in that case also, we have to take the MT as 1. But in our case, this h upon 2 LU parameter is 0.83. So on the basis of that, we can simply calculate the hill shape multiplier MH by directly referring to the table, or we can say clause. So as per the table 4.3, as per the table 4.3 that is given on page number 36, if the value slope h by 2 L is 0.83, then we can say that by default it is saying that for upwind slope greater than or equal to 0.45, MH value is 1. MH value is 1.71. But the thing is that we do need to understand here that right now we are dealing with the separation zones also, and right now we have to deal with the clause 4.4.2 in totality. We have to consider all the clauses. So if we refer to the point number, we can say C, that is given here. So for point number C, we can say that MH value, if that slope is less than or equal to 0.05, if the slope is less than or equal to 0.05, it is 1, that we have already understood, and that is not our case, and it shall be this value if it is the other case. So in here, when we are dealing with the MH value here, so MH is basically, if we enter all the values in this particular equation, that is 1 plus h divided by 3.5 into z plus L1, 1 minus absolute of x divided by L2. And that is also valid when we're talking about the slope in between 0.05 and 0.45. But that is not our case. Our case here is that we have to deal with the equation that is 4.2, or we can say C equation. So in that case, basically this is the MH value, that is 1 plus 0.71, 1 minus absolute of x divided by L2. Now in here, basically x has been considered as 10 meter. So 1 minus 10 divided by L2. Now L2 here was basically 96. and that needs to be multiplied with 0.71. So if if we find out this particular value, then this value comes out to be basically, or we can say whatever we have calculated here, that needs to be multiplied with 0.71, and whatever we have calculated here, sorry, this is already considered here, whatever we have calculated, that needs to be added to 1. So this value comes out to be 1.64. Why? Because this value is basically less than 1, so it gives us the less number than 0.71. So that is how we can find out that the value of the MH in the separation zone, that can be considered as 1.64. Now again the clause equation comes that whether the Lie multiplier has to be considered or not. So in this case, basically, as we are in Australia, so in this particular case, our Lie factor shall be 1. So as per the equation, that we can say as per the 4.4.1c, that is 4.4.1 and c, basically the value of the MT, that is topographic multiplier, that is we can say maximum of either MH or Lie. In our case, Lie is basically 1. So MH value, the one that we have calculated here, 1.64, that is our topographic multiplier. So we can say that first of all, we have to find out the hill shape multiplier, and on the basis of that, and by comparing that with the help of Lie factor, we can simply find out the value of the topographic multiplier also. And on the basis of that, whatever we have calculated, after that we have to find out the SIT beta. Now we have already discussed a lot about all the different parameters. Now let me just revise the equation again. We are talking about the VSIT beta, that is site wind speed, is equal to VR service. First of all, we are talking about the serviceability limit state. So VR service, that we have calculated above, and after that MD is the directional multiplier. After that, MC is the climate change multiplier. MZ category, we can say that is the topography and the category and height multiplier. MS is basically the shielding multiplier, and MT is the topography multiplier. So if we calculate, if you multiply all of these equations, that is in our case VR service is basically 47. So VR service, that is number is basically 47. MD we have considered as 1. MC we have considered as 1.05. MZ category, that also we have considered as 1.05. And after that, MS shielding multiplier, that is considered as 1, and topographic multiplier, that is also like quite high, that is 1.64. So if we multiply all of these numbers, then this value should be 84.78 meter per second. And same equation, that is instead of 47, if we enter the ultimate wind speed, that is 70. So in here, instead of 84.7, we can simply add 70 and then multiply all of these numbers. Then our we can say site wind speed ultimate comes out to be 126.26 meter per second. So in our case, the maximum we can say design wind speed at serviceability, that is equal to VSIT beta. But for the ultimate limit state, as per the clause 2.3, it is said that we cannot go for less than 30 meter per second wind speed. That is at the ultimate state. So in our case, it is quite high, that is 126.26. So at this point, we have concluded that our design wind speed at the serviceability limit state is 84.78 meter per second, and at the ultimate limit state, it is 126.26 meter per second. So that is concluded up to this particular point. After that, assuming that design wind pressure, that is external wind pressure, is we can say external aerodynamic shape factor and internal aerodynamic shape factor. Now both of these factors we have not discussed till yet, but in simple word, if I want to explain you that if we are talking about the wind pressure, it is not only the function of shape and height of the building, it is not only the function of the location of the building, it is not only the function of the we can say building surroundings that particular building under the question, it is also the question of the building itself or the structure itself for which we are going to calculate the wind speed. So let us say this is the house in which we want to calculate the this particular we can say wind pressure. So it shall depend on to whether let us say in a case where this whole face is open, and the second case where we can say that there is this this whole face that is completely blocked. So in both of the cases, we can say that wind pressure shall be different. Why? Because in one of the case, the wind shall go inside and shall cause disturbance. But in other case, in the second case, what shall happen is that wind shall simply get blocked here. There shall be no movement or allowed beyond this point of the wind. So in that particular case, we can say that internal wind pressures are different, and code do help us to or guides us that how we can access or how we can take the value of the internal pressure coefficient. So in simple word, external pressure coefficient, or we can say external aerodynamic shape factor. Sorry, it is not the pressure coefficient, it is an external aerodynamic shape factor. Basically, pressure coefficient is a terminology when we refer to the American codes, or when we refer to the European, or we can say Indian codes. But in this particular case, we are talking about the aerodynamic shape factors. So in simple word, basically whatever coefficients or whatever functions of the building geometry and the slope of the roof or the height of the roof, that is basically, we can say, accounted in the form of aerodynamic shape factor, that we shall discuss in detail in the next lecture. So external aerodynamic shape factor, for external assuming it is 0.7, and for internal assuming it is minus 0.3. And there is this one more factor, that is C-dyne. C-dyne is basically, we shall also discuss this in detail in the appropriate lecture. So in simple word, when we are referring to the, let us say, two kind of structures. One structure is the 100-meter height building. Second structure is, let us say, 6-meter height building. So not only wind shall exert static pressure on this building, that shall exert dynamic pressure also on this building. Dynamic pressure means that it shall change with time. Although in reality it do changes with time for this building also, but the change is very little for this particular kind of structure or for small structure. But when we're talking about the tall buildings, or when we're talking about the slender structures, so in those particular structures, we have to take the margin for the dynamic effect also. So to consider the dynamic effect, ASW170 help us to calculate the C-dyne factor also. As the building in our case is a simple building, so we have considered C-dyne value as 1. Rho air, that is density of air, that we already know as 1.2 kg per meter cube. So we can just simply find out the external design wind pressure as 0.6, and we design theta square CSHP multiplied with C-dyne. So with that, we can calculate the external design wind pressure. Similarly, for the ultimate state also, we can simply calculate this pressure again, and internal also we can calculate. And to find out the resultant, that is nothing but, we can say, external design wind pressure, that is P theta E minus P theta I. That is, we can say that whatever is the external pressure minus internal pressure, with that we can simply find out the resultant design wind pressure. Why? Because internal design wind pressure are in negative, because we are dealing with the internal pressure coefficient is negative itself. So minus minus becomes plus. So that is how we can take these values as the maximum, or we can say resultant design wind pressure. In serviceability, it is approximately 4.31 kPa, and for ultimate limit state, it is 9.57 kPa. So that is how we can calculate the design wind pressure, and we can say these directional multiplier, climate change multiplier, terrain height multiplier, topography multiplier, shielding multiplier, hill shape multiplier, Lee factors. So all of these factors has to be understood to you before you approach the real practical problems. Now there is this one more an excellent report, we can say. Basically, there is this software called Revolution, and they do provide the softwares for wind calculations and monopole design calculations. So there is this report that is given on their page, and that is free of cost. So in this particular case, they have shown their software, that how they can check or how they can calculate that. So the product is the document is given by Chris Hackney, and checkmate version is 7.2.1. So in this, basically, they have tried to access or to try to find out the various wind loads. So the first picture, that is like a very good picture to explain you in reality how the terrain category works. So let us say on the center, this is the area on which we have to construct a building. So if we are talking about the 8 cardinal directions, so these are the different 8 cardinal directions, and in if we're talking about in this particular area, let us say if you can see the cursor. So in this particular area, that is North Zone 1, we have considered terrain category 3 because there are these various buildings. We are watching the Google Earth version, or we are watching the like from the top. So that is why on this area you can see that North Zone 1, it is terrain category 3 because the buildings are very closely spaced. As we go, beyond, that is from approximately 450 meter to 670 meter, we are in terrain category 2.5. That is, we are having some obstructions, but they are like widely spaced. Again, in this area, we are having terrain category 3. Notice that in, so much dense buildings, we can see, there are many buildings. Still, we are not accounting for terrain category, we can say 4. Still we are taking the terrain category as 3 only. So that is the thing that I was trying to explain to you in the earlier lecture also. We always try to balance our we can say calculation between zone 2 to 2.5 and 3 only. In here also, up to this particular area it is terrain category 2.5, and in this particular area it is terrain category 3. But in this case you can see again, here it is terrain category 3, here it is 2.5. Again 2.53, and here it is terrain category 1 because here this is the sea. Basically you can see the water here on this particular area. So this is terrain category 1. Again this is terrain category 1, but up to this particular point it is 2, and up to this point it is 3. So there is this equation also that is given in the code regarding the averaging of the effect of the terrain categories. So we have to simply take the terrain category number and multiply it with the distance to find out the average effect of the terrain category. So on the east zone 1, it is terrain category 3 up to 112 meter approx. After that it is 2.5. After that it is 1. Similarly here also it is varying from 1 to 2.5 to 3, and here also we have already studied that it is varying between 2.5 to 3. So this is how we can decide, or you can check that whether the structure that is under the question is in which terrain category. You can refer to Google Earth also, and Google Earth is also like available free of cost, so that is not an issue. And after that it is shielding multiplier. So this is also an excellent picture that is given by Mr. Chris Hackney by Revolution. So here also you can see that basically they are taking the different value of ms from in different 8 cardinal directions. So when we are referring to east, we can say that number of buildings are very less. It is only 10. So that is why we are going into the ms1, because even if we do the calculations deep inside our instinct is that ms shall be 1 in this cardinal direction also. It has to be 1 in this cardinal direction from the north. It is 1, maybe because the buildings are like we can say quite far away from what we are considering. And in this particular area also, from this point to this point here, as per the the average value of the shielding multiplier, it has been taken as 0.8511. Here also there is no as such shielding, here also there is no as such shielding, and from this area also there is no as such shielding. Maybe there is shielding, but as per the shielding parameter that we can calculate with the help of ls divided by square root of hsps, this value does not come out to be substantial value. So that is why from this particular direction also it has to be it has been taken as 1. So in here they have calculated the hill shape multiplier and topographic multiplier for different upwind slopes and different values of h also. Basically our h shall be same because that is the height, but if you're talking about the lu, that is the horizontal distance upwind, we can say that is from the h by 2 distance that we already discussed in the earlier lecture. So that usually varies, and that has been taken as approximately 368.15. So as per that, mh value has been calculated 1.16, and the value of mt also has been same taken as the value of mh. That is topographic multiplier has been taken as same as what we have calculated for hill shape multiplier, that is 1.1684. Similarly for here also we have calculated in the same proportion for here this part also and for this part also. So what I am trying to just convey here is that for if you're referring to all the 8 different cardinal directions, we have to deal with a lot of math here. So usually we can go for the maximum, or we can say the conservative approach also. But if we are dealing with a very big project in which we can save some money, so it shall be better if we can refer to the individual directions also. So I hope the the concept is now clear to you, that how we can calculate the shielding multiplier as per the software also, that is Checkwind, or we can say Google Earth also, and how we can calculate the terrain categories also. And as I was discussing that for terrain category averaging, you can refer to basically clause 4.2.3 that is given on page number 31. So in that particular table, they have given that how we can do the averaging of terrain categories and terrain height multipliers also. So I hope the question, or we can say the practical example that we have discussed earlier regarding the value of the VR or regarding the different parameters is now clear to you. If you have any question, then I shall request you to please go through the lecture again and we can discuss that in the question answer section also.